So I'm going to take this mold cavity in as an example, and we'll show you you can work with simple or complex geometries with a breeze using VisualCAMc for Onshape. So I have a part modeled in Onshape, and I'm going to go to the VisualCAMc tab. I've already loaded the part in VisualCAMc just to make it a little faster for the purpose of our demonstration today. So the part is automatically going to preload since it was loaded and saved on the VisualCAMc tab, so you don't have to go through the process of reloading the part. So the part has been loaded, and this document is in millimeter units, and you can see that the model units is set to millimeters in VisualCAMc. And I'm going to go into Mill, and in the Tools tab, I have two tools already saved in here. And then I'm going to define the workflow very similar, define the post processor in here. I'll choose Haas as the post processor for the discussion here today. We'll select the post. We'll go in and define the stock material. We'll do a box stock. And now we're ready to generate some toolpaths. So first step, define the coordinate system origin for machining, and then the work 0. You can output your work offset number. Hit save. Go to Tools tab. You can load a tool library if you want to bring in your own tool library in here. And you can even drag and drop tools. If you want to do a facing operation, you can drag and drop a facing paste mill cutter. You can drop and drop additional tools as well. Now I'm going to go directly into some 3-axis toolpath methods. So under 3-axis menu, you'll find Z-level roughing, which is similar to our horizontal roughing in our desktop products. Z-level finishing is equivalent to horizontal finishing. You have parallel, radial, and spiral machining. So let's start with the roughing process. We'll do Z-level roughing. We'll pick a tool for it. We'll use the 1/2 inch or flat or 12 millimeter in this case. Set feeds and speeds, clearance. In the parameters, you can establish your cutting parameters where you can set your tolerances. Stock to leave. Under cut levels, or cut parameters, you can specify your cut patterns, your step overs. Under cut levels, you can specify your step down controls, control your entry and exit. So you have all of the controls that you've seen in our desktop product on the cloud as well. So you can control the ramp height, the linear extension distances, any advanced cut parameters, and all you do is generate. So you can see the toolpath is being computed on the cloud, and as I pointed out earlier, depending on the complexity involved, it automatically scales up and scales down the servers that are required for process your toolpaths. So you don't really need to have a very powerful hardware running on your end. It could be an ordinary, even like a Chromebook. You can run it on a Chromebook, which is basically just a very simple computer, and as long as you have a web browser, a decent internet connection, and a WebGL, that'll work for you. So the toolpaths have been generated in here. You can toggle the visibility of your toolpaths. We're going to run a simulation, right click and simulate. So there's your simulation for the horizontal roughing or Z-level roughing operation. I believe there was a question about loading a desktop tool library in VisualCAMc. If you export the tool library in a CSV format, you should be able to import them into VisualCAMc. At any time, I could do a pause, simulate to end to run through the simulation. The simulation has now been completed. I'm going to exit the simulation, and we are now ready to program some finishing operations. So we'll go to from roughing, we'll go into 3-axis finishing. We'll do a parallel finishing operation. We'll pick a ball mill tool for it, specify the parameters for cutting, and put in the step over, and then generate, create your toolpath. Now, if you'd like to contain your toolpaths to a specific area, you would do it similar to how you do it in our desktop products, where you can basically pick a region to contain the toolpaths by selecting a set of edges in here. So if you want to contain it just to this area here, I can just go pick these edges and then do a generate. Now the toolpath stays contained to an area. Or if you just hit a space bar to drop all of them and hit generate, the toolpath will be generated for the entire model. So we now generated a parallel finishing toolpath. I'm going to add a Z-level finishing toolpath in here. And I'm just going to right click on the bottom edge. So it picks the chain for a containment boundary. We'll use the same ball mill tool. I'm going to use a step over of 10% and generate it. And it's all happening in real time on the cloud. And you can see the task progress manager shows the status. It's generating the toolpath. Once the toolpath has been generated, it's receiving the data. Once the data has been received, you can see the toolpath right on your screen. Any change that you make in here will automatically be updated. So I can change the tool action control from retract to follow containment. Selecting generate will update the toolpath, and you'll see it'll minimize a bunch of these transfer motions, retract and transfer motions. So once you have all of your machining operations programmed and generated, you're ready to post-process it, very similar to how we did on the 2-axis and a 2D part. So I'm going to hit save, select the setup. To estimate the time, it's about 45 minutes to cut this part. Right click and post-process is automatically going to go ahead and download the posted output file onto your desktop computer in here. If you're running Windows or a Mac, it'll just download it and automatically use the name of the file, the document name, and the part name. And there's your posted output file ready to be sent out to your machine tool.